Dear students, I, Dr. Y. S. Dangi, going to present you a lecture on basic concepts and principles of remote sensing. First of all, let us start with introduction. We are discussing here the three basic concepts and principles of remote sensing. Remote sensing is the science and to some extent art of acquiring information about the Earth's surface without actually being in contact with it. This is done by sensing and recording reflected or emitted energy. Humans accomplish this task with aid of eyes or by the sense of smell or hearing. Reading the newspaper, watching cars driving in front of you are all remote sensing activities. Most sensing devices record information about an object by measuring an object's transmission of electromagnetic energy from reflecting and radiating surfaces. Remote sensing techniques allows taking images of the Earth's surface in various wavelength region of the electromagnetic spectrum, that is EMS. One of the major characteristics of a remotely sensed image is the wavelength region it represents. In the EMS, some of the images represent reflected solar radiation in the visible and the near infrared regions of the electromagnetic spectrum. Others are the measurements of the energy emitted by the Earth's surface itself, that is in the thermal infrared wavelength region. The energy measured in the microwave regions is the measure of relative return from the Earth's surface, where the energy is transmitted from the artificial source such as radar. This is known as active remote sensing, since the energy source is provided by the remote sensing platform. Whereas the systems where the remote sensing measurements depend upon the external energy source such as sun are referred to as passive remote sensing systems. The remote sensing is basically a multidisciplinary science which includes a combination of various disciplines such as optics, spectroscopy, photography, computer electronics and telecommunication, satellite launching, etc. All these technologies are integrated to act as one complete system in itself, known as remote sensing system. Stages in remote sensing. Number 1, data transmission, processing and analysis. Number 2, emission of electromagnetic radiation or EMR. Number 3, transmission of energy from the source to the surface of the earth and back, as well as absorption and scattering. Number 4, interaction of EMR with the earth's surface and the atmosphere while coming and going back, that is reflection and emission. Number 5, transmission of energy from the surface to the remote sensor. At temperature above absolute zero, all objects radiate electromagnetic energy by virtue of their atomic and molecular oscillations. The total amount of emitted radiation increases with the body's absolute temperature and peaks at progressively shorter wavelengths. The sun being a major source of energy, radiation and illumination allows capturing reflected light with cameras and films, detection and discrimination of objects or surface features, means detecting and recording of radiant energy reflected or emitted by objects or surface material. Different objects return different amount of energy in different bands of the electromagnetic spectrum incident upon it. This depends on the property of material, shape, size, structural, chemical and physical, surface roughness, angle of incidence, intensity and wavelength of radiant energy. Everything in nature has its own unique distribution of reflected, emitted and absorbed radiation. If these spectral characteristics are ingeniously exploited, they can be used to distinguish one thing from another. The process of remote sensing involves an interaction between incident radiation and the objects on the ground. This is explained by using following 7 elements. Note, however, that remote sensing also involves the sensing of emitted energy and the use of non-imaging sensors. Energy source or illumination. An energy source is required for remote sensing, which illuminates or provides electromagnetic energy to the object under study, radiation and the atmosphere. The interaction of energy with atmosphere takes place while coming to earth, and once again the same thing happens in the atmosphere after reflecting back from the object to the sensor. Interaction with the target. Energy radiated through the atmosphere interacts with the target, which depends upon the properties of both the target and the radiation. Recording of energy by the sensor. The scattered or emitted energy from the target is sensed by the remote sensor fitted in the satellite, which collects and records the electromagnetic radiation. Transmission, reception and processing. The energy recorded by the sensor has to be transmitted, often in electronic form, to a receiving and processing station, where the data are processed into an image in the form of hard copy or digital. Interpretation and analysis. The processed image is interpreted visually or digitally or electrochronically to extract information about the object which was illuminated. Application. Finally, the information which we have extracted from the imagery about the object is utilized in order to better understand about the object and to reveal some new information or assist in solving a particular problem. Electromagnetic radiation. First requirement of remote sensing is to have an energy source to illuminate the object. This energy is in the form of electromagnetic radiation. Fundamentally, these radiations behave in predictable manner according to the basics of wave particle motion theory. We are discussing here the basic concepts and principles of remote sensing. Electromagnetic radiation consists of an electrical field which varies in magnitude in a direction perpendicular to the direction of propagation, and a magnetic field oriented at right angles to the electric field. Both these fields travel at the speed of light. Two characteristics of electromagnetic radiation, that is wavelength and frequency, are very important for understanding remote sensing. The wavelength, as designated by the Greek letter lambda, is the length of one wave cycle, which can be measured as the distance between successive wave crests. It is usually measured in meters or some factor of meters such as nanometers, 10 to the power minus meter, or micrometer, that is 10 to the power minus 6 meter, and centimeter, that is 10 to the power minus 2 meters. Frequency refers to the number of cycles of a wave passing a fixed point per unit of time, and is normally measured in hertz, equivalent to 1 cycle per second, and various multiples of hertz. Wavelength and frequency are expressed by the following formula, where C is equal to wavelength, that is lambda, multiplied by V, where C is the speed of light and V is the frequency in cycles per second, and lambda is wavelength. Therefore, the two are inversely related to each other. The shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. Understanding the characteristics of electromagnetic radiation in terms of their wavelength and frequency is crucial to understanding the information to be extracted from remote sensing data. Electromagnetic energy radiates in accordance with the basic wave theory. The theory describes the electromagnetic energy as traveling in a harmonic sinusoidal fashion at the velocity of light. although many characteristics of electromagnetic energy are easily described by wave theory. Another theory known as particle theory offers insight into how electromagnetic energy interacts with matter. It suggests that electromagnetic radiation is composed of many discrete units called photons or quanta. The energy of photon is Q is equal to hc divided by lambda is equal to h multiplied by lambda, where Q is the energy of quantum and h is the Planck's constant. The electromagnetic spectrum. It ranges from the shorter wavelengths including gamma and X-rays to the longer wavelengths including microwaves and broadcast radio waves. There are several regions of the electromagnetic spectrum which are useful for remote sensing. The ultraviolet or UV portion of the spectrum has the shortest wavelengths. As its name refers, this radiation is just beyond the violet portion of the visible wavelengths. However, UV is largely scattered by Earth's atmosphere and hence of used in the field of remote sensing, but some Earth's surface materials like rocks and minerals are studied under this portion of spectrum because they show fluorescence or emit visible light when illuminated by ultraviolet radiation. The radiation which can be detected by our eyes, our remote sensors, is a part of the visible spectrum. The visible wavelengths cover a range from approximately 0.4 to 0.7 micrometer. The longest visible wavelength is red and the shortest is violet. Common wavelengths of what we perceive as particular colors from the visible portion of the spectrum. It is important to note that this is the only portion of the spectrum we is associate with the concept of colors. Blue, green and red are the primary colors or wavelengths of the visible spectrum. They are defined as such because no single primary color can be created from the other two, but all other colors can be formed by combining blue, green and red in various proportions. Although we see sunlight as a uniform or homogeneous color, it is actually composed of various wavelengths of radiation in primarily the ultraviolet, visible and infrared portions of the spectrum. The visible portion of this radiation can be shown in its component colors when sunlight is passed through a prism which bands the light in differing amounts according to wavelength. The next portion of the spectrum is the infrared or IR region, which covers the wavelength range from approximately 0.7 micrometer to 100 micrometer, more than 100 times as wide as the visible portion. British astronomer William Herschel discovered this in 1800 that the infrared region can be divided into two categories based on their radiation properties: the reflected infrared and the emitted or thermal infrared. Radiation in the reflected IR region is used for remote sensing purposes in ways very similar to radiation in the visible portion. The reflected IR covers wavelengths from approximately 0.7 micrometer to 3 micrometer. The thermal infrared region is quite different than the visible and reflected infrared portions, as this energy is essentially the radiation that is emitted from the Earth's surface in the form of heat. The thermal IR covers wavelengths from approximately 3 micrometer to 100 micrometer. The next portion of the spectrum is the microwave region, from about 1 millimeter to 1 meter. This covers the longest wavelengths used for remote sensing. The shorter wavelengths have properties similar to the thermal infrared region, while the longer wavelengths approach the wavelengths used for radio broadcast. The main advantage of this spectrum is its ability to penetrate through clouds. Radio waves greater than 1 meter in wavelength is the longest portion of the spectrum, mostly used for commercial broadcast and Meteorology. Interactions with the atmosphere. Before radiation used for remote sensing reaches the Earth's surface, it has to travel through some distance of the Earth's atmosphere. Particles and gases in the atmosphere can affect the incoming light and radiation. These effects are caused by the mechanism of scattering and absorption. Scattering occurs when particles or large gas molecules present in the atmosphere interact with and cause the electromagnetic radiation to be redirected from its original path. How much scattering takes place depends on several factors, including the wavelength of the radiation, the abundance of particles or gases, and the distance the radiation travels through the atmosphere. There are three types of scattering which takes place. Rayleigh scattering occurs when particles are very small compared to the wavelength of the radiation. These could be particles such as small specks of dust or nitrogen and oxygen molecules. Rayleigh scattering causes shorter wavelengths of energy to be scattered much more than longer wavelengths. Rayleigh scattering is the dominant scattering mechanism in the upper atmosphere. The fact that the sky appears blue during the day is because of this phenomena. As sunlight passes through the atmosphere, the shorter wavelengths, that is blue, of the visible spectrum are scattered more than the other visible wavelengths. At sunrise and sunset, the light has to travel farther through the atmosphere than at midday, and the scattering of the shorter wavelengths is more common. This leaves a greater proportion of the longer wavelengths to penetrate the atmosphere. Mie scattering occurs when the particles are just about the same size as the wavelength of the radiation. Dust, pollen, smoke and water vapor are common causes of Mie scattering, which tends to affect longer wavelengths than those affected by Rayleigh scattering. Mie scattering occurs mostly in the lower portions of the atmosphere, where larger particles are more abundant, and dominates when cloud conditions are overcast. The final scattering mechanism of importance is called non-selective scattering. This occurs when the particles are much larger than the wavelength of the radiation. Water droplets and large dust particles can cause this type of scattering. Non-selective scattering gets its name from the fact that all wavelengths are scattered about equally. This type of scattering causes fog and clouds to appear white to our eyes because blue, green and red light are all scattered in approximately equal quantities. That is, blue plus green plus red light can be called as a white light. Absorption is the other main mechanism at work when electromagnetic radiation interacts with the atmosphere. In contrast to scattering, this phenomena causes molecules in the atmosphere to absorb energy at various wavelengths. Ozone, carbon dioxide and water vapor are the three main atmospheric constituents which absorb radiation. Ozone, the harmful to most living things, serves to absorb ultraviolet radiation from the sun. Without this protective layer in the atmosphere, our skin would burn when exposed to sunlight. You may have heard carbon dioxide referred to as a greenhouse gas. This is because it tends to absorb radiation energy strongly in the far infrared portion of the spectrum, that area associated with thermal heating, which serves to trap this heat inside the atmosphere. Water vapor in the atmosphere absorbs much of the incoming long wave infrared and short wave microwave radiation, that is between 22 micrometer and 1 meter. The presence of water vapor in the lower atmosphere varies greatly from location to location and at different times of the year. For example, the air mass above a desert would have very little water vapor to absorb energy, while the tropics would have high concentration of water vapor, that is high humidity. Because these gases absorb electromagnetic energy in very specific regions of the spectrum, they influence where we can look for remote sensing purposes. Those areas of the spectrum which are not severely influenced by atmospheric absorption and thus are useful to remote sensors, are called atmospheric windows. By comparing the characteristics of the two most common energy or radiation sources, that is the sun and the earth, with the atmospheric windows available to us, we can define those wavelengths that we can use most effectively for remote sensing. The visible portion of the spectrum to which our eyes are most sensitive corresponds to both an atmospheric window and the peak energy level of the sun. Note also that heat energy emitted by the earth corresponds to a window around 10 micrometer in the thermal infrared portion of the spectrum, while the large window at wavelength beyond 1 millimeter is associated with the microwave region. Interactions with terrain objects. Radiation that is not absorbed or scattered in the atmosphere can reach and interact with the earth's surface. There are three forms of interaction that can take place when energy strikes or is incident upon the surface. These are absorption, transmission and reflection. The total incident energy will interact with the surface in one or more of these three ways. The proportions of each will depend on the wavelength of the energy and the material and condition of the feature. Absorption occurs when radiation energy is absorbed into the target, while transmission occurs when radiation passes through a target. Reflection occurs when radiation bounces off the target and is redirected. In remote sensing, we are most interested in measuring the radiation reflected from targets. We refer to two types of reflection, which represent the two extreme ends of the way in which the energy is reflected from a target: specular reflection and diffuse reflection. When a surface is smooth, we get specular or mirror-like reflection, where all of the energy is directed away from the surface in a single direction. Diffuse reflection occurs when the surface is rough and the energy is reflected almost uniformly in all directions. Most Earth surface features lie somewhere between perfectly specular or perfectly diffuse reflectors. Whether a particular target reflects specularly or diffusely or somewhere in between depends on the surface roughness of the feature in comparison to the wavelength of the incoming radiation. If the wavelengths are much smaller than the surface variations or the particle sizes that make up the surface, diffuse reflection will dominate. For example, fine grained sand would appear fairly smooth to long wavelength microwaves, but would appear quite rough to the visible wavelengths. Let us take a look at a couple of examples of targets at the Earth's surface and how energy at the visible and infrared wavelengths interacts with them. Leaves. A chemical compound in leaves called chlorophyll strongly absorbs radiation in the red and blue wavelengths, but reflects green wavelengths. Leaves appear greenest to us when chlorophyll content is at its maximum. In summer, there is less chlorophyll in the leaves, so there is less absorption and proportionately more reflection of the red wavelengths, making the leaves appear red or yellow. Yellow is a combination of red and green wavelengths. The internal structure of healthy leaves act as excellent diffuse reflectors or of near infrared wavelengths. If our eyes were sensitive to near infrared, trees would appear extremely bright to us at these wavelengths. In fact, measuring and monitoring the near infrared reflectance is one way that scientists can determine how healthy or unhealthy vegetation may be. Water. Longer wavelength visible and near infrared radiation is absorbed more by water than shorter visible wavelengths. Thus, water typically looks blue or blue-green due to stronger reflectance at these shorter wavelengths and darker if viewed at red or near infrared wavelengths. If there is suspended sediment present in the upper layers of the water body, then this will allow better reflectivity and a brighter appearance of the water. The apparent color of the water will show a slight shift to a longer wavelengths. Suspended sediment can be easily confused with shallow water, since these two phenomena appear very similar. Chlorophyll in algae absorbs more of the blue wavelengths and reflects the green, making the water appears more green in color when algae is present. The topography of the water surface, that is rough, smooth, floating materials, etc., can also lead to complications for water related interpretation due to potential problems of specular reflection and other influences on color and brightness. We can see from these examples that depending on the complex makeup of the target that is being looked at and the wavelengths of radiation involved, we can observe very different responses to the mechanisms of absorption, transmission and reflection. By measuring the energy that is reflected or emitted by targets on the Earth's surface over a variety of different wavelengths, we can build up a spectral response for that object. By comparing the response patterns of different features, we may be able to distinguish between them. Where we might not be able to, we only compare them at one wavelength. For example, water and vegetation may reflect somewhat similarly in the visible wavelengths, but are almost always separable in the infrared. Spectral response can be quite variable, even for the same target type, and can also vary with time. Example, greenness of leaves and location. Knowing where to look spectrally and understanding the factors which influence the spectral response of the features of interest are critical to correctly interpreting the interaction of electromagnetic radiation with the surface. Passive versus active sensing. So far, throughout this chapter, we have made various references to the sun as a source of energy or radiation. The sun provides a very convenient source of energy for remote sensing. The sun's energy is either reflected as it is for visible wavelengths or absorbed and then re-emitted as it is for thermal infrared wavelengths. Remote sensing systems which measure energy that is naturally available are called passive sensors. Passive sensors can only be used to detect energy when the naturally occurring energy is available. For all reflected energy, this can only take place during the time when the sun is illuminating the earth. There is no reflected energy available from the sun at night. Energy that is naturally emitted, such as thermal infrared, can be detected day or night, as long as the amount of energy is large enough to be recorded. Active sensors, on the other hand, provide their own energy source for illumination. The sensor emits radiation which is directed toward the target to be investigated. The radiation reflected from that target is detected and measured by the sensor. Advantages for active sensors include the ability to obtain measurements anytime, regardless of the time of the day or season. Active sensors can be used for examining wavelengths that are not sufficiently provided by the sun, such as microwaves, or to better control the way a target is illuminated. However, active systems require the generation of a fairly large amount of energy to adequately illuminate targets. Some examples of active sensors are a laser fluorosensor and a synthetic aperture radar, that is SAR. Characteristics of images. A few fundamental terms and concepts associated with remote sensing images. Electromagnetic energy may be detected either photographically or electronically. The photographic process uses chemical reactions on the surface of the light sensitive film to detect and record energy variations. It is important to distinguish between the terms images and photographs in remote sensing. An image refers to any pictorial representation regardless of what wavelengths or remote sensing devices has been used to detect and record the electromagnetic energy. A photograph refers specifically to images that have been detected as well as recorded on photographic film. The black and white photo of part of the city of Ottawa, Canada, was taken in the visible part of the spectrum. Photos are normally recorded over the wavelength range from 0.3 micrometer to 0.9 micrometer, the visible and reflected infrared. Based on these definitions, we can say that all photographs are images, but not all images are photographs. Therefore, unless we are talking specifically about an image recorded photographically, we use the term image. A photograph could also be represented and displayed in a digital format by subdividing the image into small equal sized and shaped areas called picture elements or pixels, and representing the brightness of each area with a numeric value or digital number. In fact, using the definitions we have just discussed, this is actually a digital image of the original photograph. The photograph was scanned and subdivided into pixels, with each pixel assigned a digital number representing its relative brightness. The computer displays each digital value as different brightness levels. Sensors that record electromagnetic energy electronically record the energy as an array of numbers in digital format right from the start. These two different ways of representing and displaying remote sensing data, either pictorially or digitally, are interchangeable as they convey the same information, although some detail may be lost when converting back and forth. In previous sections, we described the visible portion of the spectrum and the concept of colors. We see colors because our eyes detect the entire visible range of the wavelengths and our brain process the information into separate colors. Can you imagine what the world would like if we could see only very narrow ranges of wavelengths of colors? That is how many sensors work. The information from a narrow wavelength range is gathered and stored in a channel, also sometimes referred to as a band. We can combine and display channels of information digitally using the three primary colors, that is blue, green and red. The data from each channel is represented as one of the primary colors and depending on the relative brightness, that is the digital value of each pixel in each channel. The primary colors combine in different proportions to represent different colors. When we use this method to display a single channel or range of wavelengths, we are actually displaying that channel through all three primary colors, because the brightness level of each pixel is the same for each primary color. They combine to form a black and white image showing various shades of gray from black to white. When we display more than one channel, each as a different primary color, then the brightness levels may be different for each channel or primary color combination, and they will combine to form a color image. Summary: remote sensing is the science and to some extent art of acquiring information about the Earth's surface without actually being in contact with it. This is done by sensing and recording reflected or emitted energy. Humans accomplish this task with the aid of eyes or by the sense of smell or hearing. Reading the newspaper, watching the cars driving in front of you are all remote sensing activities. Most sensing devices record information about an object by measuring an object's transmission of electromagnetic energy from reflecting and radiating surfaces. Remote sensing techniques allow taking images of the Earth's surface in various wavelength regions of the electromagnetic spectrum. When the energy source is provided by the remote sensing platform, this is known as the active remote sensing, whereas the systems where the remote sensing measurement depend upon the external energy source such as sun are referred to as passive remote sensing systems. The remote sensing is basically a multidisciplinary science which includes a combination of various disciplines such as optics, spectroscopy, photography, computer electronics and telecommunication, satellite launching, etc. All these technologies are integrated to act as one complete system in itself, known as remote sensing system. Now, you have learned about basic concepts and principles of remote sensing. Thank you very much and have a nice day ahead.